Okay, today is the first day of our last chapter. It's May 15th. Can you believe that after today, you're more than halfway through May and you just got a little bit of May and some June left? It's pretty awesome. But this chapter is kind of a longish one compared to, we've had a lot of little shorties. Now this is a little bigger chapter. Today's stuff, pretty easy, but a lot of little stuff. None of it individually is hard to understand, but you got to know a lot of little stuff. And I got to spend a minute reviewing with you too. Some old stuff that gets pulled in. So, do you get that this safe is up here because there's a difference between a vector and a scalar, and the scalar is kind of like the safe. You judge a safe to some extent by how big and heavy it is. I want you to think that through. Why would a big heavy safe be way better than a small light safe? They can't just pick it up and run. Yeah, if somebody's going to break into your house and steal stuff, they can't just grab that giant heavy safe and run with it. Now, what if it takes, like, I know one, I have a relative, I'll just say it that way, who's got a safe that's really heavy. We're talking it took 4 strong people to lift the thing into the house. So you can imagine, you couldn't just like sneak in quiet at night and, with 4 guys taking this huge heavy safe around corners and stuff. It'd be almost impossible to get out of the house. And especially if you do stuff like then take the safe and chain it to whatever, now you've got something you're probably never getting out of your house. And so, anyway, so safes, basically, you can judge them a lot just by how heavy they are. All right, so do you get that has no direction to it, though? All right, so you can judge some things just based on their weight. Okay, and we do that for ourselves all the time. You get on the scale, and at least that's one of the things the doctor looks at every time you go for a physical. They take your weight, they take your height. Those are just some simple measurements, right? Those are called scalars. Get used to that term, because it's as opposed to a vector. A vector has both magnitude and direction. Magnitude is like how much weight it is, and direction, as in what direction is it going. Okay, so I like to think of a vector as like a tennis ball being thrown at you versus a golf ball being hit at you. Do you get that they weigh a similar amount, but they're shaped differently, and I'd rather be hit by a tennis ball. Okay? How about a tennis ball going 10,000 miles per hour? No thanks. Okay, so how about a golf ball going only 1 mile per hour? Yeah, it's no big deal. Probably wouldn't hurt very much at all. So it all depends on a lot of different factors, right? So if the magnitude was just weight, the weight of something moving, and I had this to represent it, okay? Do you get that I'm trying to say that these are both going in the same direction, but that the one is heavier than the other? Do you get from this, I don't know what speed they are going? So something could be heavy, but going slow. So how can I compare these two vectors? Well, at least we can say that their direction's the same, but their magnitude is different. And magnitude can be a lot of things. It could be their speed, or it could be the weight of the thing. All right, so these are kind of only 2-dimensional. Do you get that they can't even go in 3 dimensions because you can't tell X, Y, and Z direction from this? You might be able to tell X direction and Y direction, but we can't go 3D with them, and we can't tell whether or not the magnitude part is its weight or its speed. Because if the weight is equal, then this one's speed must be a lot bigger than that one's speed. You know what I'm saying? But either way, I can tell their directions are the same and their magnitudes are not the same. What if I make an exact copy of this guy? I can do that with clone. There. Now, do you get they are going the same direction and they are the same magnitude? All right. Kind of weird, but I think this has a little tail piece that wasn't copied when I copied that other part. So there. Now they're exactly the same magnitude, same length. All right, so Direction and magnitude. I'm going to play you a little clip. Does anybody remember the villain vector? It's from Despicable Me. Okay, so these are all examples of scalars because they don't have direction. Okay, moving on. These have direction and magnitude. Now, the magnitude of this could be either the weight of the plane, but the direction is just the direction. Do you get, though, that we would need an x and a y and a z to tell a direction? Yeah. The directions we're going to do today are simpler than that. They're just going to have a direction that's flat on the piece of paper. And that would imply it has an x direction and a y direction, though. Do you get what I'm saying? All right, now to make it 3D, to make it be able to leap off the page, so to speak, we would need a z direction that I can't even draw in here, but it would be coming straight out from you, from like here, towards you. And that would be the z direction. That way you can define a point in 3D space with x and y, and z comes out towards you. Or if it's going away from you, z is just negative. See what I mean? All right, so these are just two-dimensional vectors, and we are going to get to 3D vectors later. All right, a few other important things. A ton of little things that are important. First of all, there's a flaw on this. Draw over this and put an arrow only on the top, because to be a vector, it does not have an arrow. That would be called a ray. A ray has an arrow. That would be like in the old days when you learned this. If I put this up on the screen when you were in 5th grade, you'd be like, oh, it's a ray. Okay, but when they have only a lopsided one-point arrow, you know, like the point only comes back on the top side, that's a vector. Do you think the direction matters? Like, do you think BA is the same as AB? BA, is it the same as AB? No, because then it's changing what? Direction. Okay, good. Next, what if I added AB to BA? Do you get I'd be back where I started from? Well, they have to have a name for that. Normally, we just call it 0, okay? But your answer needs to be a vector, and therefore, it's the 0 vector. Now, how can you be a 0 and have direction and magnitude? They kind of cheat. They say it has a magnitude. The magnitude is 0. And it has a direction, but they don't want to just pick a random one, right? And if they have to say it has a direction, how are you going to do that? Let's say you're the mathematicians of the world and you decide, well, how are we going to explain the whole direction thing? A 0 vector. It's kind of like light and color and, well, it's every color put together makes what? Black. But how about in direction? What do you think the 0 vector is? Every direction put together. Okay, so every direction put together, do you get that they'd all kind of cancel each other out? Kind of? All right, so that's what the 0 vector is. It has no magnitude, but it has every direction. All right, I want you to turn your iPad my way so I can see that you are with me. All right, the people that are not with me, I will talk to you later. Can you be with me from now on? All right, next up, what's different between this and this? Well, one of them describes this guy, and one of them describes that guy. Are they the exact same vector? My first instinct was no when I looked at this slide, but then I realized if I take this one and drag it over onto the top of that one, oh my gosh, they exactly have the same direction. I know this is over here, but do you get they're both pointing? Like, if we wanted to say a direction like, 82 degrees or whatever, they're both pointing in the same direction as each other. So they have the same direction, and if their length is the same, which it is identical length, then if they have identical length and direction, magnitude, direction, then they're the same. They are the same. So if your answer ends up over here and looking like this, or the answer ends up over here and looking like this, it's the same. What do I mean by that? Well, if you are drawing, you know what, I'm going to show you on the next slide about how they can come out in different places, but if the answer comes out in a different place, but it looks identical in direction and magnitude, which means direction and length in this case, then they must be the same. So this guy and this guy are the same. All right, next thing, a negative vector. How would I describe this going the other way? I wouldn't say AB, I'd say BA, and then that's going like this and has the arrow on that end. But how do I do that when there's only one letter? It's really not that complicated. What do you think I do if I want to have A but in the other way? Negative A. That's all there is to it. Okay? All right, and one more thing. If you want to take a vector that's got direction and magnitude and strip out the direction part, here's what you do. You do the absolute value of it. Think about that. Do you get that absolute value kind of means, I don't care whether it's positive or negative, you know, like 6. And I do the absolute value of it, that means that it didn't matter if it was negative 6 or positive 6, it's just 6. It's kind of like stripping out the direction of whether it's positive or negative. Well, this, when you write it like that, that means I don't care about direction. All I care about is the magnitude of AB. Does that make sense to you? It takes out the direction part when you absolute value it. All right, so moving on. Here's the one where I'm going to show you. If I wanted to add A and D, first of all, do you get that those are not the same vector? Because even if they are the same length, they have different what? Direction. If I want to add them together, I can either move these two like that, and I like to think of it as a walk. I walked this far in this direction, and then I walked that far in that direction, and the result is that I went effectively from there to there, and I could have gone that way, and it would have been easier. But I would have got to the same place. That green one, that is the result. And somebody from a class has already had this. There's an official name for it. I think it might be a physics class. Do you know what that's called when you put two vectors together like that? The result is technically called, well then almost everybody in here has never said this word before, so a special moment. New word you've never said, but you're going to say again. Resultant. Say resultant. All right, I got to experience your first time of saying resultant. All right, so that resultant is the green one. Now let me show you that I could have done it a different way. I was adding those two, right? I was adding that and that. I was adding A and D, and I got the green line. Watch what I could also do. What if I leave D there and I move A over to join up? And then take a guess what's going to happen. I'm going to end up with the exact same, what do they call it again? Resultant, because it has the same what and what? Magnitude and direction. How do I know for sure? I could drag the one over the top of the other and say, oh, look. And actually, I didn't draw them perfectly straight, so they're not matching. But I think you get the idea. So it doesn't matter if you go move the A one over and touch the D, or you move the D over and touch the A. One thing you do have to remember is head to tail. Notice it's like a walk. I go from here, and then I go to the tail of this one, and then I go that direction. I think that it's good for you to think of this as a walk. All right, now, which ones, do we actually answer this question? Let's do it quick. Which ones have the same magnitude? Again, doesn't care about direction. Give me some that have the same magnitude. Degree D and F look like they're about the same length. All right, so they have the same magnitude, but they also have the same direction. Would you agree that this one and this one appear to be not just the same magnitude, but also the same direction? What does that make them? What do you think? Equal. And those two are also parallel. And they are also in the same direction. You know what I'm saying? All right. The only thing they aren't is in the opposite direction. Are there any up here that are going in the opposite direction? A and G. Very good. This guy and this guy. And if I added them together, It would end up, think of it as a walk. You would go, I'm going to take this guy and move it. Remember, I could move either one. I would walk out on the A, and then I'd walk back, and I'd end up at the same place I started, which is the what? What? Zero vector. All right, good. You're catching on, and if you're going to add A plus B, this is a good slide to do it on. And I want to remind you that on your iPad, you have the capability of drawing a line on top of a line, and then you can grab it with the lasso tool and slide it over. And then your resultant needs to be drawn. You can't just leave it like this. The resultant is like that. Now I want you to do it both ways. I just did it where I moved A over to touch B. Now I want you to try the other way also, and just leave them both on your screen, and I think you'll see that the resultants come out exactly the same. So try A plus B or B plus A, and it won't matter. I'm going to pause for a second while you give that a try. Okay, so there's really like two ways. You could say A plus B, and that's where I took this, and I moved it from here over to here, and I got the resultant vector that's green and still up here. Or I could take this and move it over and go like this, and when I draw my answer, do you get I have a vector, those two green ones are exactly the same direction and same magnitude. All right, but what I said is that B plus A is also the same thing. Now watch what I have to do for that. I'm going to draw on top of this one. And if I'm going to do B plus A, I have to start with B, and then I have to follow up with A. It's going off my screen. But I want you to just think for a second. If you could connect those, do you get it would be the same as the green line again? If I would connect it like this. Do you get it would be in the same direction? It would be the same magnitude? Can you visualize that? If you can't visualize that, I can drag it over. Because this is still the same direction, even if I move it here or here or wherever. Okay, so there's B. And here's A. And watch what happens when I connect them. Oh, it's kids right over the top of the other one. All right, I'm going to undo that, and I'm going to just take one of these guys, one of the ones that was already right, and look, if I move it in here, oh, it works again. So B plus A and A plus B are the same exact thing. All right, moving on. I think this is just more of the same. So I just want you to try one when they're kind of a little more weird. Try H. Everybody try adding A and B in part H right here. And just draw what you think the resultant vector looks like. And I want you to compare with the kid next to you. All right. I'm going to move B over and put it on A so that I'm really doing A plus B. And then it goes like that. And then I have to draw in the resultant vector. And that's like that. Was yours kind of heading northwest like mine was? Now, if I needed to say exactly what direction that is, do you get we need a way to say the direction instead of just kind of northwest? Well, we could, if we wanted to, figure out an X and a Y component for our direction, and then we could say it that way. You get what I'm saying? That's what you're going to come to next, is you're going to start describing these as it was -2 in the X direction and 5 in the Y direction. That's how you'll describe a vector soon. But you're not there quite yet. But do you get it would have an X and a Y component to it? All right. So there's my resultant. Raise your hand if you had the same basic resultant as I did. Okay, if you didn't, do you think I'm doing something wrong, or I think I'm doing it right? I do make mistakes, but yes. Okay, so are you saying you added A plus B differently? Yeah. And did you get a arrow that's going in the same direction as mine? You sure it's not heading northwest like mine? Because I think I'm doing it right, but you're right, I only did it one way. I did A plus B. If your theory is that B plus A would be different, I'll try that. But I'm going to move this over. Oops. I'll leave it there. I'll do it that way. And I'm going to go B plus A. Now remember, my answer should be the same as that blue arrow. Okay? So here's B plus, let me move A. And I'm going to move it over to on top of the B. B plus A ends up being that. And do you get that those arrows are same direction and the same length, therefore same magnitude? If I go put this on top of this one, you can see it better. See what I mean? All right, so A plus B and B plus A come out the same. And even if I move the B over to be with the A or move the A over to be with the B, as long as you line them up with head to tail, it'll work. All right, moving on. Do you get, if you were trying to move this safe and you grab onto one side of it, and it won't be long and you will have personal robots. Like really, it won't be long. Like when you're my age, I bet you anything you'll have your own robot. I'm serious. They're coming quickly. They're replacing a lot of jobs, even in China right now. In this valley in China, which is one of their main manufacturing areas, they're replacing whole factories with robots. And that's in China, where they can get work at like, I don't know, $8 a day, or maybe it's $20 a day, but whatever, it's a lot less than here. They can get labor cheap there, and they're still replacing their employees with robots for manufacturing. Okay, now there's some jobs that are harder to replace robots for, but there are robots coming. And Elon Musk is one of the people that's kind of on the leading edge of a lot of technology nowadays. Owner of PayPal originally, and now he's SpaceX and Tesla and some other company. Anyway, any one of those, if you were in charge of it, would be like your pinnacle of your career. He's in charge of 3 like that. Anyway, he says that AI and robots are coming, and they're coming fast, and that we should be a little bit scared about it, because this classic, once the robots become self-aware, once the robots can learn things, whoa, it's going to be a little scary to have robots running around that are smarter than you and can learn and don't have any emotions. Anyway, so your robot is helping you drag the safe. Do you get that safe is generally, do you kind of know where it's going to go? Well, it all depends. The robot's probably stronger than you. Do you get that it's probably going to exert more force than you are? So if you were exerting more force, do you get it would kind of go that direction? But if the robot is exerting more force, then it would probably kind of go more that direction. All right, well, you can do this kind of a question with vectors. So let's assume for just a moment that the robot is just trying to play nice to keep you happy, because for right now you have the off codes for the robot. Anyway, and he's trying to keep his pull at the same magnitude as you, but it's different directions. Does that make sense? How do I tell where the resultant is? Everybody, please, right now, figure out where is the resultant for this. I'm going to pause. I would suggest drawing in the arrows and moving them appropriately so you can figure out where the resultant is. Now, to extend that just a little bit more, I'd like you to draw in the resultant again by adding the red one to the blue one instead of the blue one to the red one. Do you get what I'm saying? Do it twice so you can see that even though the arrows come out in different spots, they are identical direction and magnitude. I'll pause while you do that. Okay, so here's what you should have done. I would have taken this one and moved, oh, not the robot. I'm going to move this line over here. And then I get that the resultant is, it's going to go like that. Raise your hand if yours was heading in that direction. Again, we need to say a way to say that direction, and we're going to add that tomorrow, and that's going to be like, how far this way did it go? How far that did it go? Like 7, 8, or whatever those distances are. See what I mean? And that's how we're going to be saying this green line, 7, 8, or whatever. That's the way we'll write it, not comma. We'll have it above each other. All right? So, next. Actually, we're ready for the homework. Cool. So let's get to the homework. It's quite a few pages down because it's a 3-day file. And you'll find the one that says day 1, assignment day 1. Here we go. Okay. So the very beginning of it is super simple. It's just, is this a scalar or is it a vector? Remember, if it's got what and what, it's a vector? Magnitude and direction. Good. Does the first one have a magnitude, like a distance, and the direction that it went? Yep, so it's a vector. Now, it was a little bit vague exactly what those were, but it did have direction and magnitude, so it's a vector. And the balance in a bank account. Man, you can make, if you want to stretch this and overthink it, you can make anything into direction. Like, I could make a bank account have direction by saying I took a withdrawal. Then it went down, and that's, direction. But it didn't say any of that. It just said balance of bank account. Does that have direction? No, so it's a scalar, so you write an S. That's all you got to do. Super simple. Moving on. This part. They should all have little arrows with one tip on them, and that's how you should say your answer too. I'm not going to make you go and fix all my problems to have this. It wouldn't take you that long, but you don't have to. But you do have to give your answers with a little arrow with one tip on it. So like, for instance, AB plus BC. Here it is. AB plus BC. Can't you just kind of see that that would be this guy, the resultant AC? So that's what you write. AC. And if you just wrote that, I would mark it wrong. What do I need? Arrow with the tip. Okay, good. Single tip arrow. AD plus DB. All right. That's, oops, hold on. AD plus DB. And that's this guy. And you might be thinking, wait a minute, how can I add those together? AD plus DB. Oh, wait, I drew it the wrong way. I did BD. DB. Well, then it's the resultant, right? What's the resultant that I can put on here? Like that. What's that called? AB. That's the answer to this plus that is that. So it's AB. All right. Moving on. Notice when it has absolute value bars, do you get that strips out the what out of it? Direction. So if I say absolute value of A, that means I don't care anymore what its direction was. All I care about is its magnitude. So is the magnitude of that one compared to this one, is the magnitudes the same? Are they the same length? No. They are different lengths and different directions. But this is asking about their lengths, not their directions. And they are different, so that would not be true. Okay, moving on. This one, you will need to recall a formula that I bet only one person in this room has still memorized. Why? Because we are kind of like robots. We are programmed to let go of information over time. The way your brain decides what's important is what do you keep doing. If you keep doing something every day, it remembers it really well. If you only did something once back in where are you guys? I better say 2003, then you would, probably for you, anyway. In 2000, let's make it simple. In 2011, well, I've been alive by then. If you only did it once way back then, you probably don't remember it anymore, right? So how many of you remember the law of cosines? You were tested on it this year. No, 1/2 AB thing, that's different. That is not the law of cosines. Nobody. So all of your brains performed. There's a lot of things being thrown around that are none of them, as far as I heard, were right. Raise your hand if you think you can do it from beginning to end. The law of cosines. I'm not going to. I think it'll be awesome if you get close, but I don't think anybody's all the way got it. Anyone want to give it a shot? Nobody? All right, here's my hint. A squared plus B squared equals C squared, but I have to put in a big thing in here. Does this ring a bell? There we go. -2. Finish. You can do it. Cosine of big C. Now, does it matter, the big versus the small? It absolutely does. All right, everybody write this down on this page because you'll have to use it, otherwise you won't be able to answer the question. And it's a good reminder. If we had had an angle and a side, then I would have probably chosen the other one. What's the other one? Law of sines. Do you remember that one? A over sine A, it's the law of sines after all, right? And notice I'm using big A because that's where the angles are. Sine big B, little c over sine big C. All right, good. And then that all depends on a triangle that looks like this. Honestly, if I were you, I'd write these down. You know why this comes up so much? Think about it. You got a vector going with another vector. Do you get that it often makes a triangle that is not a right triangle? Unless we happen to design them to always have right triangles, it's going to be using law of sines or law of cosines. So just a quick reminder, these two are going to be handy. And they all are based on a triangle. Seriously, draw the triangle too, or you don't know what's what. Where a big A and a big B and a big C are at the corners. And it can be any letter, can be anywhere. But then across from it has to be little c is across from the big C, little a is across from the big A, and little b is across from the big B. That's the setup for the triangle. And lastly, if you're going to use this form, because you can actually rewrite this in like a gajillion different ways for the law of cosines. So if you're going to use that form of it, C has to be the angle you don't know, or the side across from the angle. All right, so this has got to go with C is the big deal. Now, the thing that's cool about the law of cosines that the law of sines can't do is if you know all three sides, you can figure out the angles. That's the only formula we have for a non-right triangle where you can know the three side lengths of the triangles and then you can figure out the angles for it. Law of cosines. So on the whole scale of things to know, this is actually a pretty big one from pre-calc because do-get triangles are the most used shape probably for the rest of your life. Seriously. They really are. Because you have right angles all over the place. Just look in the room. There's right angles everywhere. Okay, and then are they all right triangles? No. Then this covers both right triangles and not right triangles. Those two formulas right there. And would you agree that the ACT has a ton of geometry on it? I've told you before, it's 38% geometry. What do you think is the most common shape used? The triangle. Do you think they might give you triangles that are not right triangles? Yep. And therefore, these could be handy. They're not required to know because you can figure out the answers other ways, but these would be handy. So memorize those puppies, or rememorize them as the case may be. All right, now we got to get to your homework. Wait, this was the last of the ones I needed to explain. That's it. If you get finished with this one, you're done. That'll be the last homework problem. And do fight through this one. It's not super easy because you got to use the law of cosines or law of sines, but you'll need to know that for this test. Yeah, because vectors always have right or non-right triangles. Okay, that's all I got for you.